Hello, everyone, and welcome to Lecture 18 of Computer Architecture. Today, we're going to talk about procedure calling. We're going to talk about how a procedure calls another procedure and what are the different things that need to take place. Before, let me review what we did last time. Last time, we spoke about control flow instructions. We looked at the different kinds of control flow instructions that exist in MIPS. We looked at branch instructions that go to some label in the code, that go to some instruction in the code based on a condition. And we looked at jump instructions that will jump unconditionally to some instruction in the code, but there's different flavors of that. So the branch instruction, there's two flavors of it. One that jumps if some value equals some other value, and one that branches if some value does not equal some other value. And for jump, we have instruction where we just another instruction where we jump to an address that's stored in some register. And then we have jump and link, which we briefly talked about at the end of last time, which we use when a procedure calls another procedure. So what jump and link does is that in addition to jumping to a label, it saves the return address in the return address register so that when the function returns, it knows where to return to. We also looked at how to use these control flow instructions to generate code for if statements. So we saw how when we have this if then else code, we had a branch if not equal that goes to the else statement if I was not equal j. Otherwise, it just continues executing the true branch of the if statement. We how to use these control flow instructions to generate code for loops. So this was a simple loop over here, and we saw how we can generate code for this loop by having a branch that exits the loop if the condition is false. Otherwise, we do the body of the loop and then we jump back to the condition, check the condition again. And we also saw how if our condition for the if statement or the loop is a less than as opposed to an equality, we can combine set on less than with branch if equal 0. And using the 0 register here. And this is how we had branches based on conditions that were not equal or not equal. After that, we had procedure calling, and we said that when a function calls another function, or if we compile these down to low-level assembly, when a procedure calls another procedure, what happens is that there's various things that the caller, which in this case is foo, has to do, and that the callee has to do to make sure that they provide each other with the data that they need, and also that they know where to go and they know where to return, etc., and that they don't overwrite each other's data. So here what we said is that the caller needs to put the arguments in special registers for the callee to find them. We said that the caller needs to jump to the callee, and here we use jump and link. We said that these local variables, z for example, needs to be put in a saved register, so we need to make sure not to overwrite the saved register of k. So we need to save the save register of foo, which is going to store k. So we need to make sure that to save k somewhere before using the same register to store z. We said that then we kind of do the work of the procedure. And then what happens is that the callee, which is bar, has to put the return value somewhere where the caller can find it. So there's a special register for that. And then we use jump register to return to the caller. So we're going to look at these in more detail today. We're going to do an example of these. Based on this, we looked at different register names. So we looked at the argument registers, which are used for arguments, the V registers, which are used for return values. We had seen the T and the S registers before, but what we said last time that was more specific about the T and the S registers is that all procedures will use both the T and the S, or can use both the T and the S registers. So when a procedure calls another procedure, there's a division of responsibilities about who's supposed to save what. So the caller is supposed to save the temporary registers if it is using any, and the callee is supposed to save its caller's saved registers if it needs to use those saved registers. And then we also said there are these other pointers, GP, SP, and FP, which we'll talk about today. And then finally, the return address register, which tells the procedure where to return after it's done. we're going to look more at procedure calling. We'll look more at the stack and things and the global variables and things like that, and we'll also do some examples. But before I start talking about procedure calling today, any questions about what we covered last time? Anyone have any questions? Everything's clear from last time? Okay, great. So moving on to today. So the question that we saw last time that there was a whole bunch of data that we need to back up when a procedure calls another procedure. And the question is, where do we back this data up? So if you recall, when a caller calls a callee, it needs to use the A registers to put the arguments for its callee. It needs to use the return address register to put the return address for its callee. And also it needs to save its temporaries in case the callee needs to use these temporaries so that the callee doesn't overwrite its temporaries. So we said that the caller needs to save the arguments, the return address, and the temporaries somewhere before making the call. We also said that the callee, if the callee is using any saved registers, it needs to back up its caller's saved registers before using the saved registers. Okay, to make sure it doesn't overwrite the caller's saved registers. So it needs somewhere to do this backup. And then also we said that there may not be enough saved registers for a procedure, any procedure, caller or callee in this case. There may not be enough saved registers for a procedure to put all its local variables, right? So if a function uses many local variables, when we compile that down to a procedure, there may not be enough saved variables to put all the local saved register to put all the local variables. So in this case, the local variables that are not going to fit in the registers, we also need somewhere to put them. Okay, and the somewhere in all three of these cases, the somewhere where we put the arguments and the return address and the temporaries before making the call, the somewhere where we back up our caller saved registers, and the somewhere where we spill the saved registers that do not fit, the local variables that do not fit in saved registers, that somewhere is called the stack. Okay, so in memory, there is this notion of a stack, and when a procedure calls another procedure, it creates a new entry on the stack, and every procedure, whatever does not fit in its registers or whatever it needs to back up for whatever reason, it will put it on this stack. Okay, so let's talk about the stack. And before I talk about the stack specifically, let's talk about the memory layout of a process in general. When a program runs, it uses a whole bunch of memory, and it has this address space, right? Addresses are 32 bits, so the program can address 2 to the power 32 different memory locations. Okay, and what we do is these 2 to the power 32 different memory locations, or these 4 gigabytes that a program has access to, are divided as follows. So starting from address 0, I'm going to put 0 at the bottom here. Starting from address 0, there's the first segment of this memory. If this is the entire memory that a program can address, this is the entire 2 to the power 32 bytes, or the 4 gigabytes. If the first part here at address 0, there's a segment, and this part is reserved for the operating system. Okay, so this part is in the program's address space. However, the program cannot really access it. The operating system accesses it, and the operating system needs it to do a whole bunch of things related to making sure processes are not interfering with each other and they know where to find things and things like that. And you study all about this in CMPS 272, the operating systems course. So we're not going to go into what goes in here in this course, but it's just good to know that this part is reserved for the operating system. Okay. The next segment is called the text segment, and the text segment is used to store the program instructions. Okay, so like we said before, a program loads instructions from memory and executes these instructions. So obviously, we need to have a space in memory where we put the instructions of the program. And that space in memory is over here after the segment that's reserved for the OS. we have a text segment that's reserved that we use to store the instructions of the program. Okay, and for the program to find out where to get these instructions from, there's actually a register which is not part of our 32 registers that we can use in our instructions. It's a kind of a separate register on its own. That register is called the PC, the program counter, and the PC usually points somewhere inside of this text segment depending on what instruction we are executing at that point in time. Okay? So the PC is the program counter. We will talk more about the PC later, but I'm just mentioning it here because it's in the figure. Okay. The next segment after the reserved segment and the text segment is the static data segment. And the static data segment is used to store global variables. So if you've written C or C++ code before, you know that you can put you can declare global variables outside of all the functions, and all the functions can access them. Well, these global variables are static data. They live throughout the entire execution of the program, and any function can access them. So we have a special segment for them. We call it global variables. And by the way, this also includes things like constant arrays, strings are usually treated like global variables. Constant, I mean here constant strings, and also static variables. So if a variable is static inside of a function, then all instances of that function can access it. You guys have seen this when you studied C++. So usually that is also treated as a global variable. Okay. Now for the program to know where to find all these global variables, we have a GP register, and this GP register, or the global pointer register, is a pointer to this static data segment. Whenever a program accesses a global variable, what the compiler does is that it uses the GP register, and it knows the offset of all the different global variables inside of this text segment. So it accesses the GP register using kind of load word or store word, and also some constant offset. Okay. The next segment is the dynamic data segment, or the heap, and this segment is used for all dynamic allocations, right? So if you're writing Java code, or C++ code, you write new, you allocate a whole bunch of data. Or if you're writing C code, you write malloc and you allocate a whole bunch of data. So the amount of data that you allocate dynamically changes over time. So you allocate more and more and more, and you start freeing, you have less, then you have more, and then you have less. So this is why the dynamic data segment starts after the static data segment, but then it doesn't have an end, right? It just keeps on growing. Okay, it can grow or it can shrink because the amount of dynamic data changes over time. Obviously, the static data doesn't change over time. You know, we are the global variables. We know what they are before we run. We don't create new global variables as the program runs. Same thing with the instructions. The instructions are fixed. We don't create new instructions while the program is running. And that's why the text and the static segments are fixed. But then the heap, or the dynamic data segment, increases with time. So it starts over here, but then where it ends just depends on where we are at that point in the program and how much we've allocated, how many times we've called new, and the size of the data that we allocated. Okay. And then finally, and what we're most interested in today is the stack. So the stack is used for what we call automatic storage, or in other words, for procedure data. So where the procedure is going to put all its arguments, where it's going to back up its arguments, where it's going to back up the saved registers, where it's going to back up the temporary variables. This location is called in memory is called the stack. And the stack actually starts at the highest address in memory. So it starts at the address which is all ones, and it grows downwards. Okay, and then the stack pointer, we have this notion of a stack pointer is going to point somewhere in the middle of the stack, depending on the current size of the stack. Right, the more we call functions, the stack starts to increase, and we'll see that later. And then when we return from functions, the stack size starts to decrease. Okay, so the stack pointer is going to point somewhere inside of the stack. And that's why we put the stack at the very end, and we have it grow kind of in the opposite direction of the dynamic data. That way we can grow the stack as much as we want. We can grow the dynamic data as much as we want. Of course, provided that the dynamic data and the stack don't collide with each other. So if they collide with each other, that means we've run out of memory. Okay? So the key point here is that we have the stack. The stack starts at the address 11111111, so all ones. And every time we want to allocate something on the stack, we kind of decrease the stack pointer and we allocate things. Okay? I will talk a little bit more about the stack in the next slide, but any questions so far about these other segments, the dynamic data segment, the stack data, the text, or the reserved segment? Any questions? Is everything clear? Okay, so then let me talk a little bit more about that. So the local data on the stack, every procedure has a frame on the stack. Okay, we call it a frame. Okay, every procedure has a frame on the stack where the procedure will store its data, the data that it needs to back up or the data that doesn't fit inside of the registers. Okay, now when a procedure calls another procedure, so let's say we had some procedure here, we have a frame pointer here that points to the beginning. So we have a frame pointer that points to the beginning of a procedure's stack frame. And we have a stack pointer that points to the end of a procedure's stack frame. So here we have a frame pointer at the beginning and a stack pointer at the end. And when a procedure calls another procedure, what happens is we're going to update the frame pointer now to point to the beginning of the next procedure stack frame, which is where which was the end of the original procedure, the caller procedure's stack frame. And we're going to update the stack pointer to point to allocate however much memory we need for the data that we need to store. So what are the things that we store on the stack frame? Well, we're going to store the arguments if we need to. We're going to store the return address if we need to. This is in the case where we need to back them up if we're going to call another procedure. We're going to store the save registers if we need to back them up. And then also if we do any dynamic local memory allocation. So if you kind of allocate an array as a local variable and it has a dynamic size or even a static size, that array is going to go over here, right? So for example, if in your code you declare a of 8, okay, you do like int a of 8, you put 8 in square brackets, you're basically allocating 8 integers, right? But those 8 integers are only going to live during that procedure, during that function's lifetime, and then after that they will go away. So you're going to put those on the stack frame for that function. Okay, so you have a frame pointer that points to the beginning and a stack pointer that points to the end. Okay, so there's gonna be one simplification we're gonna do in this course to kind of simplify the code that you need to write. And that simplification is so the reason we have both a frame pointer and a stack pointer is because when we need to access these the arguments and the return address and other things from the stack, we need a fixed register to access it from, because we're gonna have a register and an offset. But the stack pointer a lot of times will change throughout the duration of the function because the function might do dynamic allocation on the stack. However, for this course, we're going to assume that we're not going to do any dynamic allocations on the stack. We're only going to allocate things on the stack at the beginning of a procedure. And for this reason, what we're going to do is we're going, for simplicity, is we're not going to use the frame pointer. We're just going to use the stack pointer. Okay, we're just going to use the stack pointer. So when we're going to ignore the frame pointer in this class. Every time we want to allocate something on the stack, we're going to increment the stack pointer. Every time we want to deallocate something from the stack, we're going to decrement the stack pointer. Actually, because we're going from a high address to a low address, we're actually going to decrement when we allocate, and we're going to increment when we deallocate. Okay, so it's actually the reverse of what I said. Okay, any questions about the stack? Is it clear to everyone? Okay, well, if there are no questions, then let's go back. Let's go back and do finally an example of a procedure calling another procedure. Okay, we've talked a lot about procedures calling procedures. We've seen the different things that need to be done. We've seen the layout of the stack. So now let's see when a procedure calls another procedure, what needs to be done. Okay, let's start with a leaf procedure. So let's start with a function that does not call any functions and write the corresponding MIPS code for the procedure that implements that function. Okay, so let's say we have a function here, leaf example. The function is going to take 4 integers as arguments, where it's going to declare a local variable, and then it's going to do f equals g plus h minus I plus j. We've seen this before, and then it's going to return the result of f. Okay, so this is what the function does. So the first question is, we have this function, we want to compile it to a procedure. What we need to do is we need to decide where all the different variables are going to go. Okay, so the first question is, so here, G, H, I, and J, where are these parameters going to go? When this procedure wants to access G, where does it find them? Right, exactly. So we said before that we have special registers that are reserved for the arguments of a function. Okay, so here G, H, I, and J are going to go in A0, A1, A2, and A3. Okay. All right, what about F? So here F is a local variable. So where is F going to go? What am I going to do with F? Right, I'm going to put F in a saved register. So I'm going to assign F, since I only have 1, I'm going to start with S0. So I'm going to assign F to S0, okay? But there's an important thing here, which is that this function, leaf example, is probably going to be called by another, right? And that other function that's calling it might be using S0 for something else. So before this function leaf example can put f in S0, can reserve S0 for f, back up whatever it was in S0, and then restore it at the end of the function. Okay, so in order for leaf example to use f to store S0, it needs to back up whatever was in S0 somewhere, and then it can use S0 throughout its function, and then before returning, it needs to restore S0. Okay, and where is it going to back it up? It's going to back it up on its stack. And then finally, one thing to note is that after we calculate f equals g plus h minus I plus j, we're going to be returning f. So where do we need to put the value that we're returning? We're going to put that value in v0. Okay. No, I'm not talking about where we're going to return. I'm talking about where we put the value that we're returning. Right. There's the value that we're returning. There's the address that we return to. The value that we're returning is going to go in the v register. The address that we return to, we can find in the RA register. Okay, so these are a few things to note. Now, given these notes, let's go and generate code for this leaf example function. Okay, so I'm going to put it up here, and what we're going to do is we're going to generate code for it. Okay, all right, so I want to generate code for this function. I want to write the corresponding procedure. Well, the first thing I need is when a caller is going to call this function, it's going to use jump and link, right? So it's going to jump to some label. So the first thing I need is I'm going to need some label for this function for the caller to jump to, okay? So sometimes it's convenient to just make the label the name of the function. So here we're going to have leaf example, colon, and this label indicates that this is the location to jump to if you need to call this function. Okay, great. So now we have this label. Now we need to begin the function. So what is the first thing that we need to do to when we start this function? Okay, someone is asking, couldn't we just have put f inside of t0? Yes, we could have. We could have put f inside of t0 and avoided having to use any saved registers. But then this wouldn't make our example interesting. Okay, so you're absolutely right. We could have put f in t0, but we're going to put it in s0 just so that I can demonstrate a point. okay? But that's a very good observation. Okay, back to generating code. So first thing we do is we have a label for the function. Now what we need to do is we need to see if we're going to need to allocate any stack space. So do we need any stack space for this function? Do we need to put anything on the stack? So what are the different things we might need to put on the stack? Well, there's several things. First is if we are calling another function, we would need to back up our arguments and our return address on the stack. But in this case, we're not calling any other functions, so there's no need to allocate space for the arguments and the return address on the stack. Okay, so no need for arguments and return address. How about save registers? Well, what we see is we're going to need to use a save register for f. And what that means is we need to back up our caller's save register on the stack before we can use a save register for f. Okay, so we are going to need to allocate stack space. How much stack space do we need? We need enough stack space to store the old value that was in S0. So we need enough stack space to store one register. So how many bytes is that? 4 bytes, exactly. So what we're going to do is we're going to save S0 on the stack. Okay, we need 4 bytes to save S0 on the stack. How do we do that? Well, first thing is we need to allocate stack space. So we have a stack pointer. We're going to increment that stack pointer by how much space we need. So in this case, we need 4 bytes. So we're going to increment the stack pointer by -4. So we're going to do add immediate SP -4. Why -4? Because the stack starts at the highest address and goes downwards. Okay, and that's why we're going to decrement by 4 when we need a space, and then we're going to increment by 4 to deallocate that space. So I increment the stack pointer by 4, and now what I can do is I can store the old value of S0 on the stack, and the way we do that is using store word. So we're going to do store word S0 at 0 offset from the stack pointer. Okay. Okay, great. So now I've backed up S0 on the stack. Now it is safe for me to use S0. Okay. So now that I'm done setting up my stack, the next thing to do is to go ahead and execute the body of the function. Okay. So what we're going to do is we're going to have the procedure body over here. What's the first thing that we do? We want to do f equals g plus h minus I plus j. So what's the first thing that we do? Come on, guys, we've done this before. If I want to do f equals g plus h minus I plus j, what is the first thing that I do? Right, I want to add g and h. I want to add g plus h and put that result in a temporary, exactly. So g plus h are in A0 and A1. So I'm going to add A0 and A1 and put the result in a temporary. We can use T0. So we're going to do add T0, A0, A1. So this means that T0 equals A0 plus A1, or in other words, T0 equals G plus H. Okay, right, what do we next? Then we do I plus J, exactly. So we're going to do I plus J are in A2 and A3. So we're going to add A2 and A3, put the result in another temporary T1. So we do add T1 equals A2 plus A3. And then what do I do with the result? So now I have T0 for G plus H and T1 for I plus J. I'm going to subtract them. And where do I put the result? I'm going to put the result in F. Where is F? F is in S0, exactly. So I'm going to do S0 equals T0 minus T1. So sub S0, T0, T1. Okay? Great, so now I'm done with the body of the procedure. Now I need to return. Okay? So before I return, what do I need to do? I need to put the return value somewhere. right? So now I need to return f. So to return f, that means I need to take the value f and I need to put it where my caller can find it. So where do I put my return value? Right. So I need to put my return value in v0. So I'm gonna need to do a move operation. And remember, before we said that we don't have a move instruction, we just add 0, and that is our way of moving. Okay. So what we're gonna do is we're gonna put the result in the return. We're gonna get the return value. The way to do that is gonna do add s0 and 0 and put the result in v0. Okay. So now I've put the return value inside of v0 for my caller to find it. Now what do I need to do? Now I need to finally return. Okay. Now to return, there's several things I need to do. I remember before what I did is I saved my callers s0 on the stack and I've overwrote it. So what I need to do before returning is I need to restore s0 on the stack from the stack. Okay, so just like I saved s0 on the stack, I changed the stack pointer and I saved s0 on the stack. Now I need to reverse this operation. I need to get s0 back from the stack and I need to deallocate the stack space that I allocated. So how do I do that? So to save s0, I did store word s0 0 sp. So to get it back, what do I do? Right, exactly. I'm just going to load it back. So here I had store word s0 0 sp. Now I'm going to do load word s0 0 sp. So now my caller's saved variable has been restored. So now my caller will not know that I used that saved variable and that use s0. Okay, and then after that I need to deallocate the stack space that I allocated. So what do I do? Right, I'm going to do add sp4. Okay, and again, to deallocate, I'm going to add. To allocate, I'm going to subtract, and the reason is that the stack starts at the highest value and grows downwards. Okay, so now that I've restored s0, now I've restored the stack to what my caller is expecting it to look like. Now finally I can return back to my caller. And how do I return back to my caller? How do I know where to return? Right, so the return address register tells me where I need to return. So I'm going to use jump register to return back to the return address register. Okay? And by doing this, what I've done is I've implemented a complete procedure for this function up here. Okay, and this procedure takes care of finding the arguments where they're expected to be, of making sure to allocate and deallocate stack space appropriately, and returning to my caller once I am done, and making sure to put the result in v0 where my caller is expecting it to be. Okay. Any questions about this example? Does anyone have any questions? Clear? Everything's clear? Okay, great. So now that this example is clear, let's do a slightly complicated example. So what we did is we did an example for a leave procedure that wasn't calling any other functions, any other procedures. Now let's do an example for a procedure that does call other procedures. So here what we're going to do is we're going to implement factorial. So here we have this function factorial. If n is less than 1, it returns 1, else it's going to return n times factorial of n minus 1. So it's a recursive function. So here this procedure calls another procedure. It doesn't matter that there is recursion. It could have been calling a different procedure. But here, just for simplicity, we're just going to have have it call itself. Okay. Okay, so what are the things to note here? Well, the things to note are the argument n is going to go in A0. However, because this procedure is going to call another procedure, when it calls this other procedure, it's going to put n minus 1 in A0 for the callee procedure. However, it needs to use n, right, inside of the function after it returns. And for this reason, what it needs to do is it needs to back up its own argument. Also, when it calls this other procedure, what's going to happen is it's going to use jump and link, which is going to change the return address. However, the caller procedure, when it is done, it needs to know where to return, so it needs to back up its return address. Okay. So what fact is going to need to do at the very beginning is it's going to need to back up its arguments and its return address on the stack, so that when it calls another procedure, it doesn't lose those values. Okay, so that's one important thing to note. Another thing here, we don't have any saved variables. Okay, so for simplicity, there's no saved variables, there's no local variables, so we're not going to use any saved registers. But if there were local variables, we would need to use saved registers for them. Okay, but here, just to simplify this example, we don't have any saved registers. If we did, we would also have had to back them up on the stack. Okay. And then finally, like before, we're going to store the result in V0. So after we calculate n times fact of n minus 1, the final result is going to go in V0. Okay, so given this, let's go and implement or generate the low-level MIPS code for this high-level function over here that's doing factorial. Okay? Okay, let's do that. So what is the first step? Well, the first step is, by the way, I don't have enough slide space to include the function and the MIPS code. So what I'm going to do is I'm going to alternate back and forth between the two slides. Okay, so the first thing we need to do is we need to have a label for factorial so that the caller function knows where it has a label that it can jump to. Okay, so that's the first step. What's the second step? What is the first thing that I need to do when I begin executing a procedure? What did we do in the previous example? Right, we need to allocate stack space, okay? The first thing you need to do is you need to allocate stack space. And like I said on the previous slide, there are two things that we need to save on the stack. We need to save the arguments. In this case, we have one argument, which is A0, and we need to save the return address, okay? So what we're going to have to do is we're going to have to save A0 and RA. How much space do I need for A0 and RA? Right, I need 8 bytes. So what is the first thing that I do? I'm going to decrement my stack pointer by 8 bytes. Okay, and the way to do that is by doing add immediate SP minus 8. Okay, so we've allocated space for 2 registers on the stack. Okay, then what do I do? Then what I do is I'm going to save A0 and RA on the stack. So I'm going to do store word RA 4 of SP, and I'm going to do store word A0 0 of SP. Okay, so we're going to save the return address and save the argument. Okay, great. So now my stack is taken care of. Now what I can start doing is I can begin executing my my function. Okay, let's go back. So what's the first thing I do now that I've taken care of my stack? What's the first operation that needs to be done? Right, exactly. So I need to compare. I need to compare n to 1. So I want to do if n is less than 1, return 1. Otherwise, I'm going to branch to the else statement. Okay. So let's see how to do that. So the first thing to do is if n is less than 1, return 1. Okay. So n is less than 1. We're going to do set on less than. Where is n? Where here? What register? Right? And no, n is not on the stack. Well, it is on the stack, but it's also in A0. So we're going to use it from A0. We don't want to load it from the stack. So here we're gonna access n from the stack, and we're going to do set on less than the one operand is going to be n. What's the other operand going to be? It's going to be a constant. So we're actually going to use set on less than immediate. Okay, so we're going to do set on less than immediate, a0 and 1. So this checks if n is less than 1. And if n is less than 1, it's going to set t0 to 1. Okay, now what do I do? So now t0, if t0 is going to be 1, I'm going to continue to the next instruction. If t0 is going to be 0, so if the condition is false, I'm going to branch to some label where the else statement is going to be. So what instruction am I going to use? Nope. Again, we don't have a branch not equal immediate. We don't have a branch not equal that takes a constant. So I'm not going to do branch not equal 1. I'm going to do branch if equal to 0. Okay? So I'm going to do branch if equal to 0, t0 and 0. So I'm going to check if the condition is 0, if the condition is equal to 0. So if the condition is false, I'm going to go to L1 where my else statement is going to be. And if the condition is true, I'm just going to continue executing the next instruction. Okay? So if my condition is true and I execute the next instruction, what do I need to do? I need to return 1. Okay? So in other words, I need to store 1 inside of V0. How do I store 1 in V0? Right, exactly. So I can do add immediate V0, 0, and 1. So I do V0 equals 0 plus 1. So here you can see another benefit of having the 0 register is if I simply want to store some constant inside of some register, I can use add immediate to do that with one of the operands being 0. Okay? Okay, so now I've done add immediate V0, 0. Okay, so now my return value is ready. Now I need to actually return. So how do I return? What do I need to do before I return? Remember, when I started this function, what I did is I allocated stack space, right? I allocated stack space. So what I need to do is I need to deallocate this stack space. Do I need to restore? I do not need to restore. Why do I not need to restore? I don't need to restore because here, the reason I backed up RA and A0 was not because my caller needed them. Okay, in the case of S0, the reason I backed up S0 is because this was my caller's S0 and my caller needed it. In this case, the reason I'm backing RA and A0 is because somewhere else in the function I'm calling another function. So I want to be able to restore them after I return from that function. Okay, so I restore RA and A0 when I return from another function, or when another function returns back to me. However, if I am returning to another function, I don't restore RA and A0. I just restore S0, the S registers. But in this case, we don't have any S registers. So what we're going to do is we're simply going to, we don't need to restore anything. We're simply going to deallocate deallocate memory from the stack. How do I deallocate? So to allocate, I subtracted 8. So to deallocate, I'm going to add back 8. So I'm going to do add immediate SP 8. And now that my stack is back to where my caller is expecting it to be, what do I do? Right, so I do jump register RA. Okay, great. So now this takes care of the if part of this the body. So if n less than 1, return 1. I've taken care of that. Now I need to take care of the case where where this condition is false. So n is not less than 1. So in this case, I'm going to branch to the else. Okay, and then what's the first thing I'm going to do in the else statement? I need to do n times fact of n minus 1. So what's the first thing to do to calculate all of this? What's the sequence in which I do these things? Right. The first thing I'm going to do is do n minus 1. And then I'm going to call fact. and then I'm going to do n times the return value of fact. Okay, so three steps. I'm gonna calculate n minus 1. I'm gonna call fact and give it the result, and then I'm going to multiply n by the return value. Okay, so let's do that one at a time. I'm going to have the else branch now. And what's the else branch going to be labeled with? Well, here, if the condition was false, I branched to L1. So here I'm going to need to have the label L1. And the first thing I'm going to do is I'm going to do n minus 1. So I'm going to subtract 1 from n. Okay, how do I subtract 1 from n? I'm going to use add immediate. Okay, now when I calculate n minus 1, where am I going to put the result? Let's go back to the code and see. I'm going to calculate n minus 1. So n is found in A0. I'm going to do n minus 1. And where do I put the result of n minus 1? Right, A0, because n minus 1, the result of n minus 1 is going to be passed as an argument to fact, to the new fact that I'm calling. Okay, so I'm going to find, so n is in A0. I'm going to find n in A0. Okay, I'm going to subtract 1, but I'm going to put the result on inside of A0 because that's going to be the argument to the new fact. Okay. What I'm going to do is I'm going to do add immediate A0 minus 1, exactly. Okay, now I've calculated n minus 1 and I've set it up as the argument for the function that I'm about to call. So I'm done with doing n minus 1 now. I need to call fact, right? So I calculate n minus 1. Now I need to call fact. How do I call fact? What instruction do I use? Jump and link, exactly. So I use jump and, so I need to call fact. So I'm going to use jump and link. And what's the argument that I'm going to give to jump and link? What label am I jumping to? Nope. I'm not returning. I'm calling a function. So when I call a function, jump and link takes a label for that function. What's the label for the function that I'm calling? It's fact, exactly. It's fact. So here, remember, I had this label over here. The reason I have this label is because if I want to call fact, I want to jump and link to this label. So what I'm going to do here is I'm going to do jump and link fact. Okay? Clear so far? Any questions? All right, so after I do jump and link fact, okay, after I do jump and link, okay, what's going to happen is that fact is going to get called, fact is going to do a whole bunch of stuff, and then it's going to return, okay? It's going to return, and it's going to put its return value inside of V0. Okay, so what's the next thing I do after fact returns? Do I just go ahead and do n times V0? Or is there something else I need to do? Let's go back and check. So here, when I called fact, I actually lost A0, okay? I lost A0 because I had to use it to pass an argument to the new fact that I was calling. I also lost my return address. And the reason is that over here, I did jump and link facts. When I do jump and link, it overwrites the return address. So the first thing that I need to do after I return from fact is I need to restore my return address and I need to restore my arguments. Okay? So what are my return address? How do I restore my return address and my arguments? Where do I get them from? From the stack, exactly. So at the beginning over here, I saved RA at 4 SP and I saved A0 at 0 SP. So now after I return, I'm gonna restore A0 and RA. And to do that, I'm gonna do load word A0 from 0 SP and load word RA from 4 SP. Okay? All right, so now after I return, my stack is back to normal. My stack is back to what I expect it to be. Now I can go ahead and do times fact of n minus 1. Okay, so someone is asking, we didn't allocate. We didn't deallocate. Right, don't need to deallocate here, right? Because we deallocate before we return to our caller. So here we're not changing the size of the stack. All we're doing is, after I did a call, I lost some values, so I need to restore those values. Okay? No, we're not going to deallocate before calling fact, right? If I deallocate, I'm going to lose RA and A0. I don't want to lose them, right? I deallocate when I return. I allocate when I get called. I deallocate when I return. If I'm going to call another function, right, I don't need to deallocate when I return. That function will do the deallocation, right? So here I do jump and link fact. So the fact that I call is going to deallocate its own data before it returns to me, right? I don't need to do any deallocation when a function returns to me. Okay. All right. So let's go back. So here, after we fact and we restored the values from the stack, I need to do n times fact times the result of the call. So where can I find n now? N is in A0. Where can I find the result of the function call? Right, it's in V0. And where do I put the result of the multiplication? Right, I'm going to put the result in V0 because that's going to be the return value of this whole function. Okay, but I'm going to do n times fact of n minus 1. N is in A0. Fact of n minus 1, the result of it is in V0. And this whole thing is going to go in V0. So I'm going to do mul V0, A0, V0. We haven't seen mul before, but it looks very similar to an add instruction. Okay, so we're going to do mul V0, A0, V0. So this means that V0 equals A0 times V0. Okay, so now that I've done the multiplication, now, right, so now that I've V0, now what I need to do is I need to return to my caller. Okay, I need to return to my caller, and we've seen how to do that before over here. So here, after we put 1 in V0, we deallocated stack space and we did jump register. So we're going to do the same thing down here. We need to return to our caller, so we're going to deallocate the stack space by incrementing the stack pointer by 8. And then we're going to do jump register to return to our caller. And with that, we have generated code for this high-level factorial function and the corresponding MIPS assembly, while observing all the calling conventions of allocating the stack, backing up your arguments, restoring your arguments after returning from a function and your return address, and then putting the return value inside of V0 and using RA to know where to return. Okay? Any questions? Is this clear to everyone? Okay, well, if there are no questions, read more about what we covered today in section 2.8. Okay, and that's all for today, and I will see you next time. Bye, everyone.